Hello. So thank you for the introduction, Ali. So yeah, my name is Zander. I'm a second-year PhD student in the Nuclear Science and Engineering Department at MIT. My research area is plasma physics. In particular, I'm developing methods of keeping plasmas in nuclear fusion reactors more stable. I'm interested in science communication because I believe a lot of good can be done by creating opportunities for people to be more informed about the technologies that impact their lives. Like this is the case in many fields, like health sciences and stuff, but like one of the largest challenges we will face over the next 100 years or so is energy generation. And unfortunately, there are a lot of widespread misconceptions about certain aspects. Particularly after working in nuclear energy for a couple of years now, to say it has a bit of a public relations problem is an understatement. So, developing a technology is only the start. You also need to get it implemented to make a real impact. And that means you need public acceptance. So doing science communication to help that along has always been a thing floating in my mind, but I didn't really know where to start. So when I heard about this JNIPER program, I was really excited to join and gain some experience doing science writing. And in this case, I got the opportunity to learn about and write about someone really cool. So the person I wrote a cover story on was Dr. Cecilia Payne-Kapashkin. She was an astronomer, a scientist, and a scholar who worked at the Harvard Observatory in the early 1920s. Before this program, I actually never heard of them before, but after learning about her and reading their story, I'm very surprised that she's not talked about more often. So she was the astronomer that discovered that stars are mostly made of hydrogen and helium, whereas at the time, like initially, the leading theory was that stars are mostly the same stuff as the Earth, so silicon and oxygen or rocks. So when she developed novel methods of measuring stellar atmospheres, it was like completely groundbreaking. And what she did was so fundamental to the field of astrophysics, plasmas, and fusion, like especially in the department that I'm in, where the observatory she worked at is just down the road. I'm shocked she isn't mentioned more often. So I'm happy that I was given the opportunity to introduce more people to the story of Dr. Payne-Kapashkin because I think it's a story worth telling. So just as a brief overview of the science, I think that this particular topic is also very well suited for the target audience of JNIPER because, it's a relatively simple question, like, why do stars shine and what are they made of? But like, once you start thinking about it, how do you actually go about finding an answer? Like the challenge can be also stated really simply, like stars are in outer space and you are not in outer space. And if you ever got close enough to actually touch a star and maybe collect a sample, your spaceship would rapidly combust, which is not a good situation for doing science. So the route you need to go down to actually get the answer is extremely interesting. One of my favorite authors is Randall Munroe, who you may know as XKCD. Like people kind of ask him simple questions and he gives answers to the best of his ability, which typically go down very convoluted routes. But his storytelling is extremely engaging and I am tempted to emulate somewhat in writing my story, or at least in the sketch illustrations of important phenomena. So yeah, like what are stars made of? Like the point is that like some of the stuff I go into is that all you can really do is analyze the starlight, but that should have pretty much all the information you need. Though at the time, most astronomers were getting the wrong answer. Why? Well, when you're analyzing the starlight, you're looking at these emission spectra of various elements, which involves an electron falling from a high energy level to a low energy level. But something can happen called ionization, where if the material is so hot, the electrons actually completely like leave the atom. So if you have a big material that's too highly ionized, you're going to get a reduced amount of these spectral lines, or they'll appear fainter. And that's where the work that Dr. Payne-Kapashkin did was really brilliant. Like she incorporated a bit of plasma physics that essentially corrected for the effects of ionization, so you can back out the actual correct amounts of elements and such. Yeah. So this gets into the other part of the cover story. We're just talking about Cecilia's identity. So she originally attended Newnham College and Cambridge University in the UK, where Like she was an excellent student and she knew she wanted to pursue being an astronomer. However, she was unable to get a job there because, again, this was the 1920s UK. There weren't many positions for women. So she left, she moved to America. She did some incredible work at one of the premier astronomical institutions in the world. And when she applied this new technique to correct for ionization and actually get the like a much better measure of the composition of a star, when she went to publish her results, she couldn't because it went against the theories of the leading astronomers of the time. Like it's really heartbreaking. In her thesis, she needed to like dismiss her own results as being spurious. And like eventually when her findings were confirmed by other like independent observations, she gained some recognition, but like she still didn't have a much improved standings in the observatory, and she was overworked and underpaid and passed up for a promotion for many, many decades. Despite all this, like she was able to put together a very successful career as a scientist, and I will emphasize that again, as a scientist. Like that's a word that doesn't have a gender. In her autobiography, she wrote that she thinks like science publication should be anonymous and that the work should just speak for itself, which kind of puts us in a while writing this cover story, there was always a balance that you need to keep in mind, right? Like, I think when telling her story, you need to mention the unfair conditions she was in, but frame it in a way that emphasizes her tenacity, right? And like, in addition, make it clear that her discoveries were extremely important and what they mean for the field of astrophysics as a whole. And of course, figuring out why stars shine. So my main takeaway, the thing that I really learned from this program is that science communication is something that's attainable, like writing science communication in particular. So I feel like I personally might have the tendency to overthink things and get too caught up in worrying about tiny details that I never get started. But after actually participating in this program, I feel like it lowered the barrier to entry, and actually writing about science topics I think are cool or could help people understand important technologies are much more doable now. Another thing is, of course, writing for diverse audiences, especially when writing about a somewhat technical topic, like in order to convey the ideas to an audience that's, composed of middle schoolers who might not be well versed in certain aspects of it, it can be challenging at times. So one piece that stood out to me is thinking of kids as just tiny adults with less cumulative knowledge, Like if you need to say some piece of jargon, like explain it in a way that they can understand it. Distill it to the key points. Don't get too complex because then your message can be lost, but include enough so that they can still actually learn something. And another aspect that really stood out to me is moving from correction to connection in communication. Like if you just start out the gate telling someone that they're wrong, you're probably not going to get anywhere. You want to be a bit more gentle when doing outreach, like expose them to new ideas, give them all the information that they need, nudge them in a particular direction, but let them come to their own conclusions. So yeah, I think it's been fun. Thank you very much.
Thank you, Zander. Let's take a moment to thank our speaker.
So I'm going to be discussing, this is the name of the person that I am studying, who I will talk about, or I guess not studying, I wrote a story about. I'll talk about them in a little bit, but I've titled the talk tentatively, "The Importance of Being True to Oneself." So that's kind of, keep that in mind as you're watching this. So as an introduction to me, I met a lot of people last week, I guess. So for the people who I didn't meet, hi guys, I'm Cai. I'm a non-binary physicist and a fledgling science communicator, and recently, like 4 weeks ago or so, graduated with my master's in physics from University of Colorado Boulder, working with Jessica, who I think is here, and also Bethany Wilcox. This is a picture of my cat. He's a very important part of my journey through science. His name is Percy, named after the Perseus constellation, because he's a black cat with white spots. Big on astrophysics. So I've been very involved in science communication during my time at CU Boulder. Part of this interest stems from the fact that I'm the only scientist in my family. So my entire life, I've had to explain every single thing I've done to people who aren't scientists, who aren't going to become scientists, and have to find creative ways of sharing things that are a little bit maybe more complex than they are familiar with in ways that they can understand. I've also always been very passionate about science. So I talk a lot about these sort of topics. Every time I learn something new, I love to share it with people. And I think sharing what we love with others is part of what it means to be human. So I think science communication is an important thing to develop, work on, make more central to physics as a whole, because being able to share what we are talking about, what we're passionate about as physicists with a wider audience of people, I think is important to making physics seem attainable and more human, which I think is important. At CU, I did this in a couple of different ways. So one of them was through an outreach program called PhySec, which maybe people have heard of, but we do work with mostly, at least the part of it that I did, with elementary school students through middle school students. We take fun hands-on activities to sites. We encourage the kids to kind of explore and play and then talk about what they've learned in their own words. And I also have been involved with teaching algebra-based physics, where we have to take complex physics topics and explain it to people who, again, aren't going to be physicists, will never be physicists, in a way that makes it feel accessible and understandable. For this project, I picked Alan L. Hart, who is a person who has been traditionally overlooked. So he lived in the 1920s. Not a lot of people know about him. I don't know how many people have heard of him in this audience. I had heard of him once a long time ago in reference to like trans individuals from history. As a trans person, I have very few trans mentors in my life. And so I wanted to write about somebody who has been overlooked and is trans, hopefully to provide some students with those sorts of mentors and uplift this story, which is not particularly well known. I'll talk a little bit more about his story, but I found it somewhat frustrating and somewhat inspiring. I think there were a lot of things that we can take away from like how he persevered through the different challenges that he faced, that, you know, apply and can extend to other people. But he also, you know, faced some hardships throughout his life. His path was not easy. All right. So Alan L. Hart, Dr. Alan L. Hart, is not actually a physicist. He is a physician, but he wore a lot of different hats. So he was a troublemaker as a kid, author, fisherman, scientist, doctor, traveler, communicator, et cetera, et cetera, et cetera. The thing that he is most notable for is taking X-ray technology, which at the time in the 1920s was used almost exclusively to diagnose broken bones. And they had recently discovered that you could use it to see tumors, and applied it to detection for tuberculosis. So at the time, tuberculosis was the #1 killer in the United States. And there were no methods. Now it's something that's treatable with enough notice and medication, but at the time, there were no methods for dealing with it. So the best preventative measure was early detection. And that was the main thing that they could do to actually like improve quality of life. So he looked at X-ray technology and said, hey, maybe we can use this to diagnose tuberculosis before it gets too far. And that actually worked. So one of the things about him was that he worked at a bunch of different places all over the United States, traveled around. Had a lot of different jobs. So while he was a doctor on the West Coast, he did a lot of like formative work with this technology, but then he took a break to go to Montana of all places and administer medicine to farmers who couldn't afford healthcare. He traveled the United States doing a lot of communication about to sort of reduce the stigma around people who have tuberculosis. He was really big on helping people understand the disease and also creating places where people could go to get better without facing sort of fear of discrimination or anything like that. he, like, the sort of line here is refused to settle in one place with one goal or for anything less than his true self, which I found really inspiring. One of the things, or I guess several things that I learned about writing the cover story and had to apply here is this idea of letting the subject speak for themselves. So Alan Hart was an author in addition to the number of other things, a fiction author. And he wrote a lot about his time as a child, sort of under the guise of writing about other people. And so one of the things that he said about himself was that Alan spent a lot of time in the tool room making all sorts of things that would never go, which I thought was a very creative way of discussing sort of ingenuity and childlike wonder. I think another important part of the cover story, sort of what Zander talked about a little bit, is this idea of balancing your work and your life. There are a lot of important things about his life, and there's a lot of important things about his work, and finding the right balance between those two things, as important as it is in our daily lives, was very important in writing this story. And then my final sort of thing was not assuming the knowledge base of your audience. So I didn't know much about tuberculosis before this project. Now I know a lot about tuberculosis. I don't know how much you guys know about tuberculosis. My guess is probably not too much. So not, assuming that people know anything about this, that's like a very, it'd be kind of a silly thing to do, especially for kids. So balancing like understanding and explaining topics and making sure that I'm not assuming that anybody has the same experience was very important while going through this project. So that's sort of what I wrote about. What's next for me? I'm actually imminently about to move across the country. Like next Monday is when I start my moving journey, which is kind of insane to wrap my mind around. I'm not at all prepared. So I'm moving to upstate New York. So if you live there, hello. And I'm hoping to continue pursuing science outreach and communication in a future career. I'm very excited about getting involved in those sorts of things. So yeah, that's it for me. I just like to thank the fellow JNIPER Fellows and Ali, Tamia, and Claudia, and the greater JNIPER community. I've had a great time being involved in all of this. So thanks.
Thank you so much, Cai. Again, let's thank our speaker. So our next speaker is Cara. So I'll hand things over to you, Cara.
Thanks. Yeah, so I'm Cara Giovanetti. I am a rising fifth-year PhD student at NYU. And so I thought I would just share some tips and tricks that I picked up over the course of the JNIPER Fellowship. So just to give a little bit of background, I can share a little bit who am I as a science communicator. I'm mostly a talker. I've done a lot of public talks. I've done some podcasts. This picture here in the upper right was taken of me just on Tuesday evening. And so this is mostly the modality in which I'm engaging with the public. I also have done a little bit of writing, and I remembered that I really like writing, and so I've been trying to do a little more of that. So this is an article that I wrote for Scientific American, but it was about evolutionary biology and not physics. This was like honest to God science journalism, and I felt way out of my depth through this process. Like I was like interviewing experts and things. And so this was a little much, and so I was looking for some other opportunities to get involved with science communication in like written form. And so I hopped into this JNIPER Fellowship where we were asked to write these cover stories for the PhysicsQuest kits. So I was taking a look at the 2010 PhysicsQuest kit. It's mostly focused on like forces in motion. And my impression of this was like, okay, well, middle and high school students don't really get super excited about those like blocks on ramps types of problems. Those are not really the things that inspire people to go into physics careers and things like that. And so my challenge that I posed to myself is how can I make this quote unquote household physics more interesting? So I thought back to what kinds of things got me interested in physics when I was in like middle or high school. And for me, it was really like open questions in the field of physics. And so I said, okay, what is like an open question I can talk about that's somehow related to forces in motion? And the example that came to mind for me as a dark matter phenomenologist is the question of what is dark matter? And so just in case you're not super familiar with those avenues for dark matter discovery, we can look at like simulations of galaxies and things, or a prediction for how stars might move through a galactic halo. We expect that without any dark matter, just like very simple, like gravitational physics tells us that we expect things to move very slowly as you move away from the center of the galaxy. But with dark matter, you see things spinning a lot faster. And so this second picture over here is sort of the one that we observe. And so this is some evidence that we have among a lot of other evidence for the existence of dark matter. And so with this in mind, I thought, okay, I will focus my cover story on Vera Rubin. So I'm sure most of us are sort of familiar with her. I guess so the American Institute of Physics has something like, it's like 24 hours of recorded interview with her, spread over 3 separate interview sessions. And so I read all of those transcripts and tried to distill things down into something that I could use for this like middle school cover story. And along the way, along the way, I picked up some tips and tricks that I can now share with all of you. And so this first trick I think is maybe kind of obvious, is that no one wants to read walls of text. And so it's good to break things into small chunks wherever possible. So what you're looking at now is the screenshot of the V1 of my draft, which is obviously much, much, much too long to present to a middle schooler. But what's nice about the PhysicsQuest kit is that the 2010 kit had the Spectra comic that Allie was showing us in the very beginning of the coffee hour today. And so I was able to just break up the story into the same chunks that the Spectra comic was broken up into in the original kit, so that the students would, you know, read part 1 and then do an activity, and then read part 2 and then do an activity, and so on and so forth. In particular, this opened up a lot of opportunities to use cliffhangers. And so to give an example of that, part 3 ends with the sentence, but later in her career, Dr. Rubin made a discovery that would change physics forever. And then you just have to sit with that cliffhanger until you do the next activity and get to part 4. And so this kind of propels students through the kit and makes them a little more excited to see what comes next in her story. The next tip I have is something that's definitely really helpful. It was not obvious to me when I started writing, and it was really helpful for me to articulate this this little tip. And it's really helpful, especially when you're writing for younger audiences, but it's also good for older audiences. And it's replacing like first and third person pronouns with the second person pronoun wherever possible. And so version 1 of my draft had this paragraph, okay, but Dr. Rubin loved astronomy. She first noticed that the stars in the sky changed their position throughout the night, etc., etc., etc. Version 2, I changed this sentence to ask the reader, have you ever noticed that the stars in the sky change their positions throughout the night? And so even, you know, it doesn't really matter if they have or haven't, but it invites the reader into the story and gets them to consider their own experience alongside the experience of the subject. And we saw Cai do this in their presentation just a few minutes ago. They're asking, how much do you know about tuberculosis? And so it sort of draws you into their presentation a little bit more. Okay, and then the last sort of tip that I have to share is something that Zander also touched on, is trying to balance the subject and their work. Because I had like this enormous amount of information about Rubin's life, I felt sort of obligated to represent her in a way that she hasn't been represented previously in literature. Like I think like most biopics of her really focus on her later life when she's like doing her dark matter discovery, or they like pick a few common examples of like instances where she experienced sexism in the workplace and things like that. And so I felt some kind of pressure to draw in more of her than is usually presented in like a typical piece about her. And so it made it really hard actually to balance her and her work, because I had so much about her now and the story of her work didn't change very much. And so what I ended up doing was, so when talking about her early life, I was able to talk about her experience doing high school physics and like, you know, what her experience was like as a woman in a physics class at that time, and then balancing that with her early career, the work she was doing that was not really about dark matter, but instead talking about like motions of galaxies and how this was where she sort of got her start as a physicist. And then we do this again, where then I talk about later in her career, and then again talking about some of her experiences, and then I get into the discovery of dark matter. And so it was difficult to sort of pare things down, I think, to this level so that I could really have what I thought was a balanced perspective. I think overall, this is the thing that I felt could have been most improved in sort of the final version of the draft, but I think I'm more or less happy where it ended up. So that's all I have to share. Thanks.
Thank you, Cara. Any questions you might have, and we're going to hand it over to our last speaker, Jared.
All right, hello. There we go. All right. So first, let me tell you a little bit about who I am. So I'm an undergraduate student at MIT, but right now I'm actually on a gap year. In the meantime, I'm working in an experimental physics lab for nuclear physics, but my main interests are for astrophysics and cosmology. Now, in the meantime, also I've been doing some science communication. So in high school, I volunteered at a local observatory and helped show a lot of people, planets and some stars. This was really fun. But while I've been in college, I feel like I haven't really made as much time for that. So while I've been on a gap year, I've done a little bit more science communication. So one thing is MIT has a club that runs events like Splash. There are many colleges that run splashes where we have lots of teachers who are usually students, usually college students, teach classes to local high school students and middle school students. So I've been doing some of that. I've also volunteered at other various local events going on. For example, the one on the right is the Cambridge Science Festival. There's this one science communicator, Physics is Fun, and I was featured on his Instagram right there. It's great. So, yeah. Based on what I told you about my interests, it might not be a surprise that I chose to share the story of Henrietta Swan Leavitt. She was one of the Harvard computers in the early 1900s. So these were a bunch of women who did the bulk of the data analysis for the Harvard Observatory and really made a lot of discoveries during the time. So in particular, Leavitt discovered the period luminosity relationship for Cepheid variable stars. That happened in 1912, and this is something that we still use today and is super important. It's how we tell distances to anything that isn't immediately in our area. And all of the more distant objects rely on the period luminosity relationship for us to know even further distances. Yeah, and one very interesting thing about Leavitt that isn't super well known is that she developed deafness during her later years at college. And so most of her work was basically while she had full hearing loss. Yeah, so a couple things that I incorporated when writing about Leavitt is one thing I wanted to incorporate a hook and really draw in the audience. And so how do you do that? Sometimes share a shocking fact. So the Andromeda Galaxy is going to collide with us in 5 billion years. And this is going to blow middle school students' minds. But also just brings up a simple question of how do we know how far away that is? And this is also something that I think a lot of times is difficult in astronomy is how do we relate these important new discoveries in astronomy to people's daily lives? They often don't really see the connection. But sometimes it's just as simple as, you can look up and very easily wonder, how far away is that bright little thing in the sky? And that is the same exact question they were answering here. And with that, it's also very relevant to modern research. And so it's nice to bring in things that this is still important when we talk about how do we know how fast the universe is expanding? And that's really nice to share. Now, one difficulty that came with choosing to share about Leavitt is that there are actually very few primary sources. So she passed away in 1921 and didn't really have any interviews or any writings. And so mainly what remains from her is just the work itself. So that's the papers that she wrote, like the 1912 discovery, but also a collection of these plates from the Harvard College Observatory. So on the right, this one is one that the folks at Harvard believe Leavitt worked on and was likely used for her 1912 paper, where she shared the pure luminosity relationship, which she discovered in the small Magellanic Cloud. And you can see in the top right of that plate, it is labeled the SMC. So this presents somewhat of a difficult balance when talking about Leavitt's life and her work, because there's very little information about how she, overcame various challenges that she faced, and also just what problems she went through. And really, it's just a bunch of other people talking about how hard of a worker she was and how dedicated she was. But it's very difficult to know how she wants to be remembered herself. Right. So what's next for me is I would like to continue with public engagement throughout my career in some form or another. And I don't really know what that's going to look like, but I'm excited to see. The other thing is, a lot of the reason that I joined this program was to try to improve my storytelling skills, because while I have, done various science communication, taught various classes, I think sometimes I struggle to keep people engaged by telling a good story. And so that's something that I wanted to work on through this, and I hope to continue improving that. Okay, thank you.
Thank you, Jared. And thank you to all of our speakers. Now, with our remaining time, I want to hand it back to one of our fellows, Cara, and also I think a collaborator, Dr. Anthony Pullen, who's on the call, to talk about an exciting public engagement project that they have related to science communication at NYU. So I'm going to hand it back over to Cara and Anthony.
I'm just going to hand it directly to Anthony. I think if you want to maybe give us some background about what the project is. Thanks.
Great, thanks, Cara, and thanks everyone for giving us some time to discuss what we were working on. I guess so. Basically, what we have is 4 times a year we host a sort of something like Astronomy on Tap. With those of you who are familiar with that public outreach effort, it's a little different. We hosted at a place called Book Club Bar, which is sort of half bar, half bookstore. And it's a really nice space to give public lectures. And basically, it's a little bit different from Astro and Tap in that we focus a little bit, instead of just talks on astronomy, the talks sort of span more astronomy and particle physics, which matches with the research center that I'm a part of at NYU in the Department of Physics. Just to be clear, I guess I haven't. Just to be clear, I'm Anthony Pullen. I'm an associate professor at NYU, and so that's what a little bit different about it is. The way it started off actually was funny. So there was a student. So I teach periodically a non-majors physics course. Basically, I teach Einstein's theory of general relativity to non-majors. So these are from economists to artists to and everywhere in sort of the, I guess, the full grid of majors that exists in the at NYU. And so one of the students there was just who's a journalism major. She was just very excited about the course, and she had a friend of hers who was who helped organize Astronomy on Tap meetings in Baltimore, and they were hoping to do something similar here. So they asked if I could help with that. And so with Astronomy on Tap, most of those meetings are more in the most of those are more in Midtown to Upper Manhattan. So we decided to do something in East Village, which is, more closer to, the East Village and sort of the lower half of Manhattan. And so surprisingly, it's gone really well. So the space seats about 45 people. And all the times we've had 5 meetings so far. So one in the 22-23 school year, and then 4 in the 23 to 24 school year. And since then, they've all been sold out. And it's and for speakers, we get volunteers from the from our research center of cosmology and particle physics. Most of them are grad students, with one postdoc who also presented. And so far, it's as far as we've heard, it's been a great experience. There's always engagement after the meetings, people who continue to discuss science. One thing that we also do at these meetings is I have asked 4 or 5 graduate students to specifically stick around each meeting to talk with the guests there. So while many people ask questions during the talk, and you get some of the most curious questions, and it's very fun engaging that way. We also have people who stick around after the talk and also ask questions and just express their enthusiasm for learning more about science. And so so that's been a great experience. And so Cara, she actually gave the first public talk for this, and it was an excellent, amazing talk. And since then, although she's not officially a part of the committee we use, she's been a great sounding board for ideas, as far as helping to improve this. And so I was happy to participate when she asked if I could come here today and talk more about what our project is about. So I did fill out a part of the JNIPER assessment form, which is actually very beneficial. It helped me sort of think a little bit more systematically about what the purpose is of our meetings. How, what things do we put in? What are the outputs? Thinking about long-term impacts, risks, for our event. So yeah, that's been very helpful. And so I'll be happy to answer any questions about how our meetings are run, how to, what will we consider for future impacts of this, and how we think about running these meetings long term. One issue, of course, is always with, I think, meetings, or public events that are run with students, is that none of these people are permanent employees in our institution. So we always have to think about, the max that we will be able to have them to help out is 4 years. So we really have to think about how we continue to engage with sort of the pool of potential volunteers at our institution, to make them invested in this project, and to continue to have people who cycle in and out through in helping out with this program. And so that's always an issue. And there's and then there's just sort of practical things like keeping the venue, thinking about, should we move to a different venue? How do we maintain relationships that we have? Because, as a volunteer, as something science related, we don't want to we want to limit the resources we need to use in order to host these events. So managing relationships with potential vendors is always something that we have to be mindful of. So with that, I'm happy to discuss more, answer questions. I think Cara, who's been to all the events, in addition to speaking at the first event, also would probably have some comments as well that may be useful. And I'll be happy to, if it'd be useful to continue as a discussion for the rest of the time. I'd be happy to help facilitate that.